Okay, I'll be starting in about a minute or two. Let others also join. Okay, let's start. Am I audible? Can you confirm?
Yes, sir. Good evening, sir.
Yeah, good evening. Okay, so let me just check the camera. Okay, I hope I'm visible also. All right. So my name is Varnit Kapoor, and I'll be taking up with your tutorial sessions for the subject thermodynamics. So uh, I am a PhD student at IIT Delhi, and we'll go through the concepts from very basic to advanced level topics as well as the course taught by Professor Kale in the Nptel videos. And I'll be taking up with the doubt sessions as well. If you have any doubts, you can ask me uh, in all these sessions, which are going to held every Tuesday, 6 to 8 p.m. by me. Okay. So before starting with the subject, may I know you are a UG student, PG student, Siddhanti?
Yes, sir. I am an BE first semester student, sir, in mechanical.
B first. From which university?
I am from Vasavi College of Engineering. It's an affiliated to OUN and it's autonomous, sir.
Autonomous
Oh,
University, and which city or state?
yeah, Usmania University.
Okay, and
From
it is in which Hyderabad.
Yes, sir.
Okay, okay. So may I know like what's your motivation to join this course?
Actually, we have this subject in the upcoming semester, like we have it in the second semester. Right now,
Okay,
first semester, some exams are going on. So
okay.
the second semester will start from the 10th Feb. So it will be useful for me to gain the knowledge and it will be useful for me to for the second upcoming semester also.
Yes, yes. So have you watched the lecture videos shared on the portal?
Yes, sir. I have watched few videos, but I couldn't complete it
Okay, all right,
as
okay, no problem,
we are going through the examinations. That's why.
no problem. Okay, all right. All right, let us start. Let me share my screen. Just give me a second. Is my screen visible?
No, sir.
Not visible? Okay. Uh, Now is it visible or? Yeah, it's
Yes, sir.
visible, I guess. All right, cool. Okay, got it. So let us start. So subject is thermodynamics, very basic subjects of bachelor's dynamics. So we'll start with the basic concepts first of all. So starting with then we'll go through the first law, second law, entropy concepts, available energy, unavailable energy, and pure substances. All of these topics we'll go through. So what is thermodynamics basically? So thermodynamics is basically a branch of science. I can speak it in three different definitions. It's branch of science which deals with the you can say study of energy interaction of a system with respect to surroundings or its impact on the properties over the systems, okay, of the systems. Like if there is an energy inside or energy out going, if it is equal, then we say that it is a steady flow of energy which is happening. And if it's not, the incoming energy is not equal to the outgoing energy, then we say that it's an unsteady flow of energy. Or we can say that, in other words, it's a branch of science with which the help of which you can convert the disorganized form of energy into an organized form of energy. Okay, like you have a heat from in a turbines. Okay, for running a power plant, you convert passing that steam heat through a turbine, and you get the work out of it. Okay, so it's a disorganized heat which has been converted into a form of an organized work. Or you can say that it's a branch of science which deals with the study of three E's, three capital E's. E's means equilibrium, energy, and entropy. Okay, I'll write all these things. So all these notes will be shared on the link on the portal itself. Okay, and all these videos will be uploaded on the YouTube as well later on. All right, all of my live tutorials. Okay, some other has also tried to join. Let me see. Okay. Okay. So students will meanwhile join. Let's start. So first, write the basic concepts. Basic concepts. So first definition is that you can say that thermodynamics and from now onwards I'll write it into the short form TD. Okay, is a branch of science which deals with, and any one of you can anytime stop me. Don't hesitate to ask any kind of questions if you have. Okay, so that everything is clear. The purpose of the tutorial, live tutorial session is that which deals with the study of energy interaction. I hope whatever I'm writing is visible on the screen
Yes, sir.
of system. Okay, with respect to, so WRT is a short form for with respect to surroundings and its impact on so its impact on property of system. Okay, like you can say that energy in, energy out is equal to 0. Then you say that it's a steady flow energy happening, steady flow of energy is happening, and not equal to 0. You say that unsteady flow of energy is happening. We will discuss all these things in detail toward the later part of our course. Other words, you can say that thermodynamics is a branch of science with help of which disorganized form of energy is converted into organized form. All right. Next definition, you can say that it's a branch of science. So all these definitions are very standard definitions from the good books, which deals with the study of three capital E's. So these E's are, that is, equilibrium, energy, and entropy. We'll understand all the definitions. So as I wrote, system, energy interaction of system with respect to surroundings. So what do we mean by system and surroundings? So system is basically anything which is under consideration. All right. Anything which you are considering is a system. Okay. It's your wish what you want to consider as a system. So anything, suppose I have a pencil. So this pencil is my system. Inside that, there are a lot of IC chips, anything is installed. If I want to study an IC, that will be my system. I want to study whole as a pencil. That is a system. So it's my consideration. And basically, it's a controlled region in a space over which our attention is focused. And what is the surrounding? Everything external to the system is surrounding. Outside this pencil, everything is surrounding. Okay. So let me write. What is a system? So anything under consideration and it is also a control region in space over which our attention is focused. What is a surrounding? It's everything external to the system. Okay, everything I'm going to try to join external to the system. All right. Now, one thing is that what is a boundary? Okay, with respect to thermodynamics, boundary is nothing but which separates the system from surroundings. Okay, which separates system from surrounding. So boundary which separates system from surrounding. So if I say I have a figure like this, okay, so inside is my system, outside is my surrounding, and the separation between both of them is my boundary. Okay, all right. Boundary can be real or imaginary. Okay, so real boundaries are represented by a continuous line, which I made here. So it's a complete continuous line. Okay, no breakage is there, or a curve should be there, and imaginary lines are represented by a dotted. Okay, so it's a very important note. Boundary may be first point. Boundary may be real or imaginary. You will get to know that what are in physical meaning related to a real or imaginary thing in a short duration. Maybe real or imaginary. real boundary are represented by continuous line or curve like this. Okay, whatever arbitrary shape you can take, and imaginary boundary are represented by dotted lines. Like this. Right? Simple. This is a representation. Boundary may be fixed or movable. Okay, both conditions can be there. May be fixed or movable. Boundary may be fixed, or by fixed, what I mean, the change in the volume should be zero. Okay, it's a rigid thing. That is, change in volume dV is equal to zero and it is rigid. Okay, or movable. Some small example, a balloon, if air inside the balloon is your system, outside the balloon is your surrounding. So the layer of the balloon itself is a boundary. If you inflate more amount of air inside that, that is a moving boundary. The balloon will inflate. Okay, the boundary can move. The balloon can inflate or deflate. Whereas if your consideration is this pencil, and the pencil outer part of the pencil is a boundary, it cannot change, twist, turn, or stretch out. Simple. And in as per our assumption, we take one assumption here that it should be considered of zero thickness. The boundary should always be considered of zero thickness. Okay. All right, here. Assumption is that boundary should be considered of zero thickness. Okay. Why zero thickness? The question arises because if there is no zero thickness, there will be some energy loss which will happen. Okay. So a real practical example is that if sun rays are coming on the earth and towards your home, okay, towards a building, so the wall is acting as a boundary. Okay, sun rays are getting struck by the wall, that is acting as a boundary, and your wall has some thickness. The walls of your house have some thickness, or a building has a thickness. So there is an energy loss. That's why you feel inside a much cooler inside your home compared to the outside. Okay, very physical, basic physical example. Okay, I'll not write that. Now, what is a universe? The summation of both system and the surrounding is called as a universe in whole. Okay, so universe system surrounding. Okay. All right. Now, what are types of system? We said we understood what is a system. Okay, what is a surrounding? What is a boundary? What are kind of boundaries are available? Okay, what is a universe? Now, what are types of system? There are three types of system. One is open system, one is closed system, and one is isolated system. So what is an open system? Open system is basically where both mass and energy interaction is taking place. Like you have a turbine, you have a boiler, you have a pump. Okay, you have a pump in which you say motor in a local language. So the water flow comes from the bowel and you fill your tanks with that. So the mass interaction as well as the potential kinetic head at the pump is converted into a potential head. So energy as well as mass interaction is happening. Closed system is where only energy interaction is happening. Okay, like you have a piston cylinder in your IC engines. Okay, so there, if you have a piston cylinder arrangement where walls are not there, okay, then you can say that only mass is not going, but energy is being converted, potential into kinetic. Okay? What is an isolated system? Where neither mass or nor energy interaction is happening. Like we in a real world, we say that whole universe is an isolated system. Or on Earth, we can say that like a thermoflask is there. Okay, is an isolated system where you keep your, in real condition it's very difficult to say, but in ideal condition you can say that you put your water inside your thermoflask, hot water, and it remains hot. There is no energy change or no mass change from there. Okay, all right. So types of system. First is open system. It is a system in which both mass and energy interaction takes place. Example, you have a boiler, you have a pump, you have a condenser, okay, or all the other mechanical equipments you can say. Next is closed system. Where only energy interaction is taking place. Only energy takes place. All right, example, piston cylinder arrangement. Without walls, very important. Without walls, not with walls. Otherwise, fuel intake and exhaust will happen. What's an isolated system? Just hold on. Okay. So where neither mass or energy interactions takes place. Neither. So example, you can say the whole universe or a thermoflask. Okay. So there I have highlighted this without walls. So like if you have an IC engine or a pressure cooker at your home, okay, it can behave both as a open system or a closed system. How? Condition is that if it is with walls, then in IC engine during the suction process of the fuel and during the exhaust stroke, as I said, the mass transfer will also happen. So that's why it's an open system. Okay. But during the compression and power stroke, the walls get closed. Then that's a closed system. Okay. So the IC engine can behave both as closed and open system. Depends on the condition. That question can be asked somewhere. There is one key factor that all the open system devices are used in closed system. Okay. Why? This is an assumption that all the open system devices are used in the closed system. What is a closed system? Where only energy interaction is happening. If you have some cycle of a Rankine cycle is there, okay, of a steam turbine or gas turbine, some cycles are there. So there you see that individual components are there. Pump is there, condenser is there, compressor is there. Okay, a lot of other equipments are there. All of them behave, all the other mechanical equipments behave as a open system. But when they are in a closed cycle, then the mass is always conserved. Whatever mass exits from the pump exits from the, you can say, a turbine, enters the condenser. Okay? But only what is happening, the energy interaction is taking place. That is, the kinetic energy is converted into a rotational energy or potential energy, whatever it is. Okay? So mass interaction happens. So individually, all the components are open system, but when they are in a cycle, they behave as a closed system. So I'll write this point here, a short point. All the open system devices behaves as closed system in a cycle or a cyclic process cycle. All right, because mass interaction is happening. Any doubts still here to anyone?
No, sir.
No doubts. Gaurendra, are you there? Can you unmute yourself?
Yes, sir, no doubt.
Yeah, no doubt. Okay,
No doubt.
you are a UG student or a PG student?
UG student.
UG student. From which university?
AKTU.
AKTU. It's in which city?
Mathura. UP, Uttar Pradesh.
It's in UP. Okay. All right. Oh, great. All right. Now coming to a different kind of approach, like we say a microscopic approaches, there are macroscopic approaches. Okay. So let me write that. Microscopic approach, microscopic approach versus macroscopic. All right. So in microscopic approach, basically, you have a single particle, okay, which is under your attention. And it is also known as a statistical approach. Whereas in case of macroscopic approach, you have a time average behavior of lot of particles, molecules, which are under your consideration. So it is known as a classical approach. And from there, a concept of continuum comes. So concept of continuum says that we are taking our matter whole as a continuous without any voids. Okay? If a lot of particles are there, there are no voids between them, and all the particles behave as a continuous approach. Okay, all the particles behaving as a group, and we are studying this group as a whole. I'll write that. Microscopic approach. Single particle is under consideration. Attention. And it is also known as statistical approach. And in macroscopic approach, time average behavior of molecule is under consideration. And it is known as classical approach. All right, classical. And what's a continuum approach here? Oh, so we are taking our matter as continuous. Without any void. Like, suppose you have a group of particles. Suppose you have some particles are there. So no void is assumed. This whole group is considered altogether as a single entity. Okay, without any void. It's a continuum approach. There's a key point to note here that in, you can say, rare field gases, where the distance between the particles is more than a mean free path, and mean free path is nothing but the distance between two collisions to happen between the particles. If that path is greater than the mean free path, such gases are rare field gases. The concept of continuum is not valid there. Okay. And these are treated at a scientific level. So we won't, in thermodynamics, we won't deal with the rare field gases. So I'll write the point here. In case of rare field, isn't valid. Okay. Now what's a thermodynamic property? So property is nothing but, a thermodynamic property is that it represents the characteristics of your system. Okay, what is the characteristic? So there are different type of thermodynamic properties, basically two. One is that it's an intensive property and another is an extensive property. And intensive property which are independent of the mass, okay, like pressure, temperature, some coefficients are there, okay, or some specific quantities, okay, which are a ratio of the two extensive properties. Also, you can say specific energy, specific heats, which are independent of the mass. And the extensive properties are those which are dependent over the mass of a system, like volume, kinetic energy is half mv square, potential energy, entropy, enthalpy, heat capacities, not specific heat capacities. Okay? So all these are dependent over the mass. So suppose you have a room, okay, in if you do there's a pressure, temperature, mass, and volume of a room. Okay, some pressure is maintained, some temperature is there. If you separate the room by two in two equal halves, will the temperature change of both the rooms? Temperature will remain same. It doesn't depend if you have separated into equal halves. Will the mass, will the pressure change? No, both will have experienced the atmospheric conditions. Will the volume change? Definitely volume will change. Volume is dependent over the mass. Will the mass change? Exactly, mass is changing. Half of the mass is here of the gas which is present inside that room, and half of the mass has been shifted to the another half of the room. All right. So, right, types of let me write first. What is a thermodynamic property? So it is a it represent, I can say, characteristics of a system. Types of properties. So first one is intensive, or you also say it as intrinsic. These are the two words, intrinsic. So properties that are independent of mass. All right. Example, pressure, temperature T, okay, some conductivity K, specific terms, or ratio of two extensive property as well. Ratio of two extensive properties like density. Okay, mass and volume. Density is mass over volume. So mass itself is a extensive property. Volume itself is extensive property. Both the ratios will be, both of the division will be a ratio of density, which is an intensive property. Okay, like density. Oh, okay, or you can say specific energies, which are energy over mass. All right, next is extensive property. So dependent on mass. So example, all of the energies, all the energies. I'm saying energies, not specific energies. Make sure. All of the energy like kinetic energy, potential energy, then entropy, enthalpy, okay, or you can say volume, heat capacity. So I'll make a short diagram here. So if you have a room and you divide this room into halves, so the pressure will automatically be same in both the chambers. Temperature will be same. Mass will be divided in two, and volume will be divided in two halves. Okay. All right. Now let's come through to the definition of thermodynamic equilibrium. What's a thermodynamic equilibrium? So system is said to be in a thermodynamic equilibrium when they are in thermal equilibrium, mechanical equilibrium, and chemical equilibrium. So all these three properties should be satisfied. All these three equilibriums should be maintained. Then you can say it's in a thermodynamic equilibrium. I'm not just saying equilibrium, it's a thermodynamic. So thermodynamic equilibrium. So system is said to be in thermodynamic equilibrium when they are in thermal equilibrium, EQ, I'm writing the short notation, mechanical equilibrium, and chemical equilibrium. What is thermal? Thermal equilibrium means equality of temperature has been achieved. Chemical means equality of chemical potential has achieved, and mechanical is equality of mechanical forces or pressure has been achieved. Yes. Okay. So thermal is equality of temperature. This mechanical is equality of uh, forces and pressure. And chemical is chemical potential. Right? All right. Okay. Any doubts still here?
No, sir.
No doubts. Okay. Just give me a minute. I'll just join back, please. All right. Now, what's a pure substance? What is a pure substance? Pure. It's nothing but a substance of constant chemical composition. The composition should be constant throughout the volume, which is irrespective of the phase, whatever phase it is. Is it in a solid phase, liquid phase, or a gaseous phase? Okay. So, like if you have a ice, water, or steam, it has same composition, that is H2O. Ice plus liquid again has the same composition. Liquid or steam together, ice, liquid, or steam all together, all have H2O inside. The same composition irrespective of the phase they have. Also, like a dry air or gaseous air, all of these fall under a pure substance. But there's a point to note that atmospheric air or a moist air is not a pure substance. Dry air or a gaseous air is a pure substance, but atmospheric air or a moist air, which we say, is not a pure substance. Why? Because the atmospheric air has some percentage of water vapor inside that, which can vary from one place to another place. Like in the southern part of India, the moist air has a different amount of water vapor compared to the northern part of India or a western near to the coastal areas or near to the mountains. So atmospheric air or moist air have different amount of percentage of the amount of vapor inside that. It's not uniform throughout the whole earth. Okay. So some place it's a high humidity, some place you say it's a low humidity. So that's why atmospheric air or moisture is not a you can say a pure substance. But in thermodynamics, we will treat this moist air as a dry air for our assumptions. Okay. But in refrigeration subject, when you will read, okay, then there is a concept of relative humidity. There you won't consider dry air or moist air to be same. All right. So let me write pure substance. It is a substance of constant chemical composition throughout its volume of minimum. Okay, its volume of minimum quantity, whatever, irrespective of phase. Example, you have ice, liquid H2O, or steam. or you can say ice plus liquid H2O again has H2 only. All of them has H2 only. Or if you take liquid H2O plus steam, any of the combination all have H2 only. Also, you can say dry air or dry air or gaseous air. All of them are pure substance. Okay, pure substance. Whereas atmospheric air or moist air isn't a pure substance. Pure substance because percentage of water vapor content varies at from place to place. Okay, high humidity or low humidity. But we will assume that it's an assumption as well that we will consider this air as well as a pure substance. Now, what's a thermodynamic state? So it represents a condition of the system. What is the condition at that point? What is the pressure? What is the temperature? Okay. Path is nothing but which is obtained by joining the two equilibrium states, two equilibrium thermodynamic states from point A to point B. How have you reached? That is your path. Okay. Let me make. So thermodynamic state. So I'm using short form TD for thermodynamic. It represents the condition of system and what is path obtained by joining sorry take a voice isolation obtained by joining of two equilibrium states. So suppose you have a PV plot, pressure versus volume plot. Okay, pressure versus volume. Where P is the pressure and V is the volume. The initial state is like this: P initial, and this is your P final. Okay, and this is your V initial, and this is your V final. The graph looks like something like this. So from initial point to a final point. Okay. So initial and final are your states, initial state and final state, and this is your path. That's how you reach there. Okay. So I can make this plot to be like this. Okay. Now, what is a reversible process and an irreversible process? An irreversible. So process is said to be reversible in which your system returns to the original state without leaving any effect on the surroundings. Okay, there is no effect on the surrounding and the system has returned to its original state. Then you can say that it's a reversible process. Otherwise, it's an irreversible process. Okay, and for reversible process to occur, both the forward as well as the reverse path should be same. So this arrow represents you are moving forward, and when are you coming back as well? If both are same, both the paths are same, then you can say that it's a reversible process. If both are not same, then it's an irreversible process. Okay. And reversible processes are represented by continuous lines, whereas irreversible processes are represented by dotted lines. Okay. Okay, one more thing to tell that why we plot P pressure versus volume or temperature versus entropy plots. One thing is that because we deal with heat and work interactions. Okay, and they give us, these plots give us the heat and work out of it. Always remember, like this is a pressure versus volume. So what is work? I'll write a short note here. What is a work? Work is nothing but force into displacement. Okay, and what is force? Force is nothing but pressure into area into displacement dx. Some displacement is there. So basically area into dx is nothing but your volume, change in the volume. So P dV is your work. All right. So this is a pressure, this is a volume. So pressure versus volume plot is required in that sense. Okay. So some small keynote you can have. Right. Okay. Why we deal with PV and TS plots. So process is said to be reversible in which system returns to its original state without leaving any effect on surroundings. Okay. Note, for reversible process to occur, both forward and reverse path are same. And reversible process are represented by continuous lines practically in real life scenarios. Nothing is a reversible process. Okay, and irreversible are represented by dotted. You will see in the plots, coming plots, that how the representation occurs. Like one I can make here, that if you have a PV plot, short PV plot. So if it's a reversible process, that means something like this, and both the paths are same from state 1 to state 2. Okay, it's a reversible forward path are both same. Whereas if you have another kind of PV plot, which is represented using dotted line, that means the process is not reversible. All right. That is why I have not drawn the arrow here. Paths are not same. Example of irreversible process, every real life scenario, because friction is involved everywhere. Okay, friction, wherever friction is there, or a free extension, mixing of fluids is happening. Heat transfer through a finite temperature difference. All of these are the example of irreversible processes. Examples of right here. Is that friction, free expansion, mixing of fluids, or heat transfer through a HT is a short form for heat transfer through a finite temperature. Difference. Okay. Any doubts still here? Varinder?
No, sir.
Clear? Everything is clear?
Yes, sir.
Okay. Now, what's a cyclic process? So a process is said to be a cyclic process in which the initial and final state are same. Okay. So when you start from a point and you reach back to the same point, that's a cyclic process. Cyclic process. Where a process is said to be cyclic. In which initial, final states are same. Okay. Note to keep here is that minimum processes required to make a cycle are two. Two processes should be there. One cannot be there because it will be otherwise infinite number of processes are there. Like minimum processes required to make a cycle are two. If there is a, it cannot be one. In this, infinite number of processes will happen. Like if you say it's a circle, both the states are same. How will you define that the initial and final state are same? All the points will be same. So there can be infinite number of points. The infinite number of processes can be there. So that's why. So for two processes, like one you can have, if you have a PV plot like this, pressure versus volume plot is something like this. You're going like this and coming back like this. Okay, it's not an irreversible, but it's not a reversible, it's an irreversible process. But still, for a process cycle to happen, there should be two processes, from 1 to 2, then from 2 to 1. Okay, or you can say somewhat like second is one process is like this. Okay, so suppose this is it's a three process cycle. It's a pulse jet engine cycle, which is called as linear cycle. One from 1 to 2, then from 2 to 3, and then from 3 to 1. Okay, it's a linear cycle. Third can be, it's a two process cycle. First one is a two process cycle. Second one is a three process cycle. Third, you can have a four process cycle, which is nothing but your Brayton cycle, which will have one is like this. Suppose like this, it's a, I should make the expansion part more wider. Okay. Somewhat like this. So 1, 2, 3, 4, four process cycle, and fourth is a five process cycle, which is a dual cycle. These are all the cycles you'll see in your subject called IC engines. Okay. It's a dual process cycle is up. 1, 2, 3, 4, 5 processes are there. Okay. Arrows are very important to mark the directions. Okay. All right, we have seen what is a cyclic process and how many processes are required for that. Now, what's a quasi-static process? You might have heard a word quasi-static. So quasi-static basically means infinite slowness. So infinite slowness is the characteristic which represent the quasi-static process. Very, 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 very small amount of infinite amount of slowness is there. Slow is the process, it's happening, and it almost represent like a rest condition. You won't be able to differentiate that the system is at rest or even moving. Okay, infinite slowness is there. So it is obtained by joining the series of equilibrium state. Every state is an equilibrium. So whole, the equilibrium is not disturbed. Okay? So it's an imaginary process. In real life, nothing is a quasi-static process. And quasi-static process without friction is happening, then it is a reversible process. It's a note to keep in mind. If friction is also absent and it's a quasi-static process, then you can say it's a reversible process. Again, which is an ideal condition. Nothing is irreversible in the real world scenarios. Okay, so right here, quasi-static process. So infinite slowness is a characteristic of quasi-static process, and it represents in almost in rest conditions. Okay, and it is obtained by joining series of equilibrium states and it is imaginary process basically obtained by joining it's an imaginary process obtained by joining. Note to keep here is that quasi-static without friction is reversible process. So if you have, suppose, a system like this, okay. So there is some piston inside this, or some weight is there. Okay, first piston is there, and there is a weight over it. Okay, you have this is an initial state of a system. Make a very short weight. This is your initial state, and your system piston has reached to a final state of this. Okay, so this was your initial state. This is your final state. Okay, how the piston has moved. You are removing the weight in a very short, infinite small amount of weight you are removing at every time. Okay, so very slow, infinite weights you are removing from here. Infinitely small weights you are removing from here very slowly. Okay, so then you can say it's a quasi-static process, and it is a series of equilibrium states. So how the pressure versus volume plot will look like for this? You have a pressure, you have a volume. So this is a pressure versus initial state. This is your final state. So it's nothing but joined with series of small equilibrium states. Okay, and series of equilibrium states. Okay, it's an irreversible process, this one, if it's because friction is present. because we know that a weight has some friction. It's a real object, and wherever it's a real object, friction will be there. Yeah, so it's an irreversible process. So some loss will be there even at some micro or nano levels. Okay, and in energy, it is basically this without friction term is written if without frictionless, because this is an arrangement. It's an assumption which you take so as to say that it's an reversible process. Okay, okay, that's clear. Quasi-static process. Now let's come to thermodynamic property. Thermodynamic property. Earlier we did, oh sorry, thermometric property. Thermodynamic property what we did. We'll come to thermometric property. Thermometric thermometric properties. So it is the property from which you can calculate the temperature. From the which you can calculate your temperature. So if you have a constant volume gas thermometer with you, where the volume is constant, then it is a property depends over the pressure itself. So temperature is directly proportional to the pressure. If it's a constant pressure gas thermometer, then volume plays the role of the thermometric property. If you have an electrical resistance kind of thermometer, then the resistance plays the role of thermometric property. For a thermocouple, if you have, then there is some effect called a Seebeck effect, where electromagnetic forces that of volume plays a role. And in an ordinary thermometer, the length or the volume of that thermometer plays a role. Okay, so you might have seen in laboratory some long thermometers that were short in your home. Okay, it is a property with help which temperature is calculated. Example, in constant volume gas, thermometer pressure, if volume is constant, then pressure plays the role of thermometric property. Plays role of TP, that is thermometric property. Since you have volume is constant, then from the relation PV is equal to MRT gas equation, your volume is constant. That this implies temperature is directly proportional to pressure. Temperature is only proportional to pressure. So that is, temperature is nothing but function of your pressure. Temperature is function of your pressure. Next is, in case of constant pressure gas thermometer, pressure gas if pressure is constant, then volume plays a role of thermometric property. Okay, that implies from PV is equal to MRT, volume is constant, so temperature is nothing but function of pressure. Third is the scenario in case of electrical resistance thermometer. Thermometer where resistance will play thermometric property. Fourth is, in case of thermocouple, EMF, electromotive forces are there. That of volume plays the role of thermometric property. Fifth is ordinary thermometer. length or volume plays role. Why volume? Because if you say you have a volume at second position, second state, and at initial state 1 is nothing but volume is nothing but area into length of L1. So area of the thermometer remains same. Okay, it's a constant cross sectional area is there, then it's nothing but dependent over length or length only. Okay, that's why it depends basically on the capillarity of the tube. Very small, 0.6 or 6 to 10 mm of diameters are there of that thermometer. Okay, any doubts still here?
No, sir.
No doubts, all clear. Great. You have seen the lecture videos earlier of week 1.
Yes. Yes, sir.
Okay. I completed the assignment as well.
No, sir. It's going on.
Okay. Now coming to the ideal gas equation. I'll take a minute. I'll just be back in a minute. Okay, let's talk further. Now coming to the ideal gas equation. So first thing, how a gas is behaving in ideal gas, it's always when the condition is of low pressure and high temperature. Whenever a gas is at low pressure and a high temperature, then that gas will behave as an ideal gas equation. Okay, so that right. Any gas behaves as an ideal gas under low pressure and high temperature. Very important statement. Low pressure and high temperature condition. Okay. Mathematical expression is that PV is equal to mRT, where temperature is always in absolute temperature in Kelvin. Okay. Pressure is the absolute pressure. Okay, net absolute pressure, and R is nothing but the characteristic gas constant. Am I audible? Hello?
Yes, sir.
Oh, so T is always, yeah, T is absolute temperature in Kelvin. Pressure is absolute pressure, that is net absolute pressure, and R is characteristic to that gas, corresponding to that gas constant. Characteristic gas constant. Okay. What do we mean by absolute pressure? Is that if I have a reference, okay, this is my reference. Should not draw like an excess. I have some state point, state reference that is said to be absolute zero pressure. If it's an absolute zero pressure condition, then any pressure which is here post this condition is an absolute pressure, is an absolute pressure. Okay, from the absolute zero pressure to up some state which it is at, that's an absolute pressure. There is some standard, that is an atmospheric pressure, which is taken as a standard around the globe. So this is a, from the absolute zero, this is a standard, that is P atmosphere, and P atmosphere is nothing but 1.01325 bar, or 1 bar is nothing equal to 10 to the power of 5 Pascal. The 10 to the power of 5 Pascal, or Newton per meter square. Pascal is Newton per meter square. 10 to the power of 5 Newton per meter square. All right. 10 to the power of 5 Newton per meter square. All right. This is your P atmosphere from the absolute zero. P absolute is from the absolute zero. What is our gauge pressure? Gauge pressure is always above the P atmosphere. So above the P atmosphere is called a gauge pressure. So in gauge pressure, already atmospheric pressure will be there. So it's a positive gauge pressure. And if you have a pressure somewhat, if you say somewhere here from the P atmosphere, it is a negative gauge pressure, or you say a vacuum pressure. What is a vacuum pressure? Less than the P atmosphere is an vacuum pressure. Okay, in the negative direction. Negative gauge pressure, or you say it's a vacuum pressure. All right. Okay, very pretty simple diagram. So P absolute will always have P atmospheric plus gauge pressure. So P absolute is nothing but P atmospheric plus gauge pressure. Okay. P absolute is sum of plus P. That's why I wrote P here is nothing but absolute pressure, net absolute pressure, which is sum of gauge plus atmospheric condition. All right. Okay. What is other form of ideal gas? One is this PV is equal to MRT. Okay. One is, another is, the other form of ideal gas is ideal gas equation is PV is equal to nRT. Okay. So here R is R bar. Okay. To differentiate, Here R bar is a universal gas constant. Earlier R was not a R bar, it was a characteristic gas constant dependent on that gas. But here R is the universal gas constant. It's universal for every gas. And N also can be written as mass over molar mass of that gas, R bar T. So if I write this together, okay, I'll take another pen. So that is M into R bar over M into T. Then this term will be your R, that is your characteristic gas constant. Because M is the molar mass of specific gas corresponding to that gas. That's why R bar over M is the characteristic gas constant, whereas only R bar is a universal gas constant. So I'll write here, this is a universal, and universal gas constant has a value that is 8.314. Okay, or in terms of another, we can also write another units as well. So this is all. R bar is nothing but R is nothing but R bar over M. So for R bar is, I'll write the value. R bar is 8.314 kilojoule per kilomole Kelvin. Always remember the units. Kilojoule per kilomole Kelvin. Okay. For air, what are the properties? These properties should be in your mind always whenever you are solving some questions. Sometimes examiner won't give these values. So for air, the specific heat coefficients CP is 1.005. CV is 0.718. R for R is a characteristic. Now for the air I'm saying, that is R bar over M is CP minus CV. That is 0.287. And the units of all these three are kilojoule per kg Kelvin. Okay, kg Kelvin. And suppose you have some gamma, it's a polytropic constant, that is Cp over Cv. For air it is 1.4. Adiabatic index, you can say. Adiabatic index. Okay. And what is a molar weight of air? It's 29 gram per mole. Exact is 28.96 gram, but we say 29 gram. Molar weight for air 28.96, which is equivalent to 29 gram per. All these should be in your mind. Another point to note is that if I'm writing small t, it's a degree Celsius. If I'm writing capital T, it is Kelvin, right? Temperature is in Kelvin. So 0 degrees Celsius is nothing but 273.15 kelvins. Okay, always remember. What is the triple point temperature of water? Triple point temperature TP of H2O is 273.16 Kelvin, or you can say 0.01 degrees Celsius. If you see, the difference is just 0.01. Okay, 0.15, 0.16. All right. What is triple point pressure of the water of H2O is 4.587 mm of Hg of mercury. 4.587 mm of Hg. So triple point pressure, I should write. This was temperature T, and this is pressure. Okay. So its pressure can also be written as, in terms of head, rho GH. Rho is 13.6 into 1000. 13.6 is a relative density to that of water. So the absolute density is 13.6 into 1000. T into 9.81 into head is 4.587, which you wrote here. 4.587, right? So it will be 611.97 Newton per meter square in absolute terms, I'm saying, or pascals. Okay, so unit is this. Always remember. Okay, any doubts in all these things?
No, sir.
Doubts? Now coming to the temperature measurement scale, how we used to measure the temperature. So before 1954 and after 1954, what happened? So before 1954, we use a method where we took two reference temperatures into the consideration. One was ice point and other was steam point, ice point and steam point. So temperature measurement. Scale. So method used before 1954 was, in this method, two reference temperature are taken into consideration. That is ice point and steam point. Okay. So ice point is for the ice, T ice. So small t means in degree Celsius I'm writing. Was 0 degree Celsius was taken as a standard. Okay. And for, so we will say that some distance it will travel over the thermometer was X of ice. Okay. Whereas steam point for the steam, it was 100 degrees Celsius. And X is here, X of steam. So it follows, it used to follow a linear variation, that is temperature is equal to A into X plus P. Okay, so for ice point, if you put an ice point, so T was 0 and AX of ice, okay, so AXI I'll write in short form, AXI, XI says I, plus B. So B was nothing but negative of A of XI. Okay, at steam point, so this was at ice point, and at steam point, temperature was 100 degrees Celsius. AXS plus B. You know that B is nothing but AXI, negative of AXI, AXS minus negative of A minus AXI. So A take out common. So from here, A comes out to be 100 over X displacement of the in the thermometer at steam point minus ice point. Okay, and B was nothing but negative of A XI. So negative of 100 XI over XI minus XS minus XI. Okay, so you can overall write this linear relation as 100 over XS minus XI into X minus XI. Okay, so this is a linear relationship. Okay, so if you have a thermometer of different materials, then the temperature of this thermometer will be showing at some different reading. Okay, if materials of a thermometer is different, then all the thermometer will measure some amount of different reading for a human body. Okay, why? Because they have different values of conductivity because of the different materials, and there are some frictional resistances for different materials. Uh, if you say honey has a higher viscosity, the higher friction inside that, whereas compared to a mercury or a water. Okay, so you also, if the same thermometer is used to separate, mark the readings at different times, okay, of the same human body. Then also there will be some difference, but standards are steam and ice points, okay, and between whatever between them is happening, that is your linear temperature variations. That's why this method was used before 1954. But after 1954, the method was of a single fixed reference state was used. That was a triple point temperature of the water. Triple point of the water, not triple point temperature, triple point of the water. Okay. So method used after 1954. So in this method, a single fixed reference state is used. That is triple point. Triple point is nothing but where liquid, solid, and gaseous phase exist all together. Okay. Of water. Okay. So in case of constant volume gas thermometer, if you take, which I wrote previously, example, in case of constant volume gas thermometer, their pressure is, temperature is directly proportional to pressure. Temperature is function of pressure. So from idle gas, PV is equal to MRT. Okay. So R here is characteristic gas constant, not universal. That's why M has been written. If N was written, that means it was a N R bar T, universal gas constant. So temperature here is K times some P, function of pressure. So K can be written as P by what? Triple point. If you take at a position of triple point, so temperature at triple point and pressure at triple point. Okay, that was your reference, and you put back this K here. So your temperature will be P of triple point, that of P by P of triple point. Okay, that was your function which was used for a constant volume gas thermometer. Okay, now what is an ideal gas thermometer? So ideal gas thermometer is nothing but a thermometer in which it is independent of the material of the construction. Whatever material you use inside that, that's an ideal gas thermometer. Okay, just a short definition for that, which obviously, for obvious reason, is not an existing thermometer. Ideal gas thermometer. So it is thermometer which is independent of on material of construction. Okay. What is 1 Kelvin? We wrote Kelvin as a temperature unit. What is 1 Kelvin? It is defined as 1 by 273.16 of triple point temperature of H2. Okay. It is so in this definition, if you say, sorry, from this ideal gas, if it's an ideal, in case of constant pressure gas thermometer, what you will write, or it's a constant volume gas thermometer, what you will write is that it is defined as 1 by 273.16 of triple point temperature of H2. So that is your 1 Kelvin. Now coming to the Gibbs phase rule. So all of these are the basic concepts which we are covering today. What's a Gibbs phase rule says? that the degree of freedom is nothing but the number of components minus the number of phases plus 2. So F is your degree of freedom, number of components minus the phases plus 2. So phase is nothing but a physically distinct, mechanically which is separable, and chemically which is homogeneous. That is called as a phase, okay? Which is physically distinct. You can distinguish between it's a steam or a solid phase or liquid phase. You can mechanically separate the liquid out of solid or a solid out of liquid, and it is chemically homogeneous. Okay, so all of that is made from H2O particles, molecules. Okay, so phase B is physically distinct, mechanically separable, and chemically homogeneous. Okay, what is degree of freedom? F here is nothing but it is the minimum number of independent variables of the intensive or intrinsic variables. You can say it's a minimum number of independent variables, or you say intrinsic or intensive variables, which are required to locate final state of a system. Okay, locate or find the, sorry, not the final state, locate or find the state of that system. Okay, so whatever is the state, you how many number of variables, you can say that just by knowing the temperature, just by knowing the pressure, or just by knowing temperature or pressure, you can tell the state of that system. Okay, so these are the minimum. Degree of freedom is the minimum intensive or intrinsic variables are required to locate or find state of system. Okay, state of any system. All right. So we know what is degree of freedom. We know what is phase. Let's take one case. It's case one. So if it's a single component, single phase system. Okay, example, if only ice is there, or water is there, or steam is there, any one of the phase you will consider, and it's a single component. Okay, so degree of freedom will be 1 minus 1 plus 2. So that means you need at least two variables to define a system. Okay, single phase, single component. Case 2, ice plus water is a scenario. Ice as well as water is there. Okay, so right here, any of these, ice, water, or steam, but this is ice plus water. So degree of freedom will be the component is only one, that is 2, but phase are 2 plus 2. So you only need one independent variable to define. So degree of freedom is 1. Case 3 is when ice plus water plus steam, all of these three are there. So here the degree of freedom will be component is 1, the phases are all the three together, and plus 2, so that is 0. So it's 0 degree of freedom is there. It's a unique reference point where degree of freedom is 0, and that is known as a triple point where all the three phases exist together. That's a triple point. So it's a unique reference point. That's why after 1954 this point was chosen. It is unique reference point having f is equal to 0 is known as triple point. Where solid, all the three phases exist together. Three phase exist. Okay. Right. Pretty much simple. Any doubts in Gibbs phase rule?
No, sir.
Clear? Okay. I'll just take a minute now. Excuse. Okay, let's resume. Now coming to point or state and a path function. Okay. Point function and a path function. Point, or you say state and path function. All right. So any variable is said to be a point function whose value doesn't depend over the path. Okay. If it is independent of the path, then it's a point function. Like pressure. Pressure at initial state, pressure at final state. It doesn't depend what path it has taken. It's a point function. Temperature is a point function. Volume is a point function. Volume initially, what was volume finally? You don't say that's volume is dependent over the path. Whereas variable whose values depend over the path has some past history, okay, like heat and work. During the from one point to another point, how much work has been extracted, how much heat has been supplied to the system. That's a path function. Okay. So point function. I'll write in this way. Variable is said to be point function whose value doesn't depend on the path followed by the system. By system. Example, pressure, volume, temperature. Whereas variable whose value depends on past history of system is, example, is a heat and work, our path function. Okay, all right. Yeah, so if we say, if I draw a graph here, a PV plot again, because we are extracting work, pressure versus volume. So this is our initial state. Initial state, it went to 1.1, and from there it came back to from 2 to 1. Okay, so if you see from 1 to 2, you say what is pressure at 1, what is volume at position 1. What is pressure as 1, what is volume at position 1. That's why pressure and volume are the point functions. What is pressure at 2, what is volume at 2. But what work has been done is dependent on pressure, change in the pressure into volume, change in the volume. Okay, so dp, if you say dp, yeah, change in the pressure over the cycle is nothing but p final or p2 minus p1, or volume change dv is v2 minus v1. What is your volume change? What is your pressure change? Okay, p2 minus v1, p2 minus p1. So that's why we can write exact, it is in the form of exact differential. Okay, dp or dv. So cyclic integral of a variable is nothing but 0. If you say from point 1 to point 2, I'm saying it has gone. But if in a whole cyclic process, I should not write here the cycle first. I should write just from 1 to 2. On 1 to 2, this is your point function states. But if I'm saying it is a cycle, okay, then your change of a variable, the cyclic integral of the variable is 0. How? Exact differential. So here, cyclic integral of variable, whatever variable you have, pressure, temperature, volume, is 0. That means in the above graph, if you do a cyclic process, from where you started, 1, you came back to the initial position 1, or 1 to 2, and then 2 to 1. Then your change in pressure will be P1 minus P1 only. Your initial state was also 1, final state was also 1. So that's why P final minus P initial, that is P1 minus P1 is equal to 0. That's a scenario you say it is a cyclic exact differential. Okay, it's an exact differential. What's an inexact differential? Where the cyclic integral is non-zero. Okay, like with the work or heat. Inexact differential. Where cyclic variable of that variable is not equal to 0. For example, for work and heat. So how we represent these notation? Q and heat and work, that is Q and W, are the path functions, and these are inexact differentials. Whereas all the properties are path point function as and the exact differential. Always make this is a note. So pressure, temperature, volume are the property point functions as well as exact differentials. But heat and work are path function and are inexact differentials. Very important note. Q and W, that is heat and work, are path function and inexact differentials. Whereas all the properties are point function and exact differential. Okay, that's why you can write dp dv. For inexact differential, you write in the notation dq but not exact, so a bar, cross bar. Okay, or dw crossed. Whereas for exact differential, you write it as dp not crossed, dv not crossed. Okay, one or the another way. For the exact differentials, representation is like this. I'll write here only dp dv, okay, dt representations. Okay, or you can also write this inexact differential to be W from 1 to A to 2. 1 to 2, one processes will follow 1 to A to 2, okay, or 2 to A to 1, whatever it is. Okay. All right. Now coming towards the last topic of our today's tutorial is the zeroth law of thermodynamics. Zeroth law. What is zeroth law? Thermodynamics. From next tutorials onwards, we'll start with the energy interaction processes. Now we understood what are basic, what is system, what is surrounding, everything is there. Yes. Do you have any doubts? You raise your hand. Gorendra?
Sir, what is the difference between heat and work?
Difference between heat and work we'll discuss. Don't worry. In the energy interactions, we will discuss all the difference between heat and work. I'm just going through the basics for now. Okay. So coming to the zeroth law of thermodynamics, is there any doubt related what I have taught so far?
No, sir.
So heat and work we will discuss in the energy interaction part. Next tutorial will definitely discuss in very detail.
Okay.
So this was given by R.H. Fowler, and according to this law, if there is a body A which is in thermal equilibrium, you remember thermal equilibrium is mechanical, chemical, and temperature. Okay, that's a thermal equilibrium with the body B. And then if a body B is in thermal equilibrium with the body C, a third body C, then you can say that body A and C are in equilibrium with thermal equilibrium with each other. Okay, so this law came because it provides a thermal equilibrium concept of thermal equilibrium base for the conduction, also convection, also in various other scenarios it can be. Okay, suppose I give you a very short example of a thermometer. So there is a thermometer, there is a mercury nib out of it. Okay, so suppose the nib of the thermometer is body B, the mercury inside the thermometer is body C, and you yourself is a body A. Okay, so when you put the body A, the human put the thermometer in its mouth. Okay, then the temperature of the mouth, the human basically, is equal to the temperature body B, that is the nib, and the equivalent rise in the mercury level is the temperature balance between the nib and the mercury. So that means your body is your in thermal equilibrium with the mercury. That's why we say that it's following a zeroth law of thermodynamics, that your body A is in thermal equilibrium with the rise of the mercury level. Very pretty basic example. So right, according to this law, when body A is in thermal equilibrium, so I'll denote it with TE, with body B, and body B is in thermal equilibrium with body C separately, not together, separately. Very important word. So that A and C are not together. Then body A, then we can say that body A and C are in thermal equilibrium with each other. So example for a thermometer, role played by a thermometer. Suppose you have a thermometer, there is a nib of the thermometer. Okay, nib, mercury inside the thermometer. All right. So that's so this is your body B. Mercury is your body C, and human. So I'm drawing some human mouth lips. So human is body. Okay, so pretty basic example. Okay, any doubts?
No, sir. No, sir.
No doubts. So all these notes will be available on the portal. If you see, I will upload the notes. There will be an Excel sheet which will be shared where you can directly click the link, and week you will see the notes. All this recording will be uploaded on the YouTube. In the Excel sheet, the link will be given, as well as on my YouTube channel only. So my YouTube channel is, I'll write here, is the name of the YouTube channel is NPTL with Varnit. This is my YouTube channel. Okay, right. So even all this sheet will be there where the links will be there for the enrolled course students, and in the description also I'll put the link of description of the YouTube video. I'll put this link of the sheet even if you don't find anywhere. So I expect that more of the students also join from the coming sessions, and like this will be going on. And if you have any doubts in the coming session, you can ask me. I just hope that people are regular in the sessions. Okay. All right. So can we end the session here?
Okay, sir.
Okay. So I'll see you in the next tutorial. Next Tuesday, every Tuesday, 6 to 8 p.m.
Okay.
Okay.
Thank you, sir.
Thank you.